Close your eyes for a moment, if you can. Imagine a mountain, not a dramatic, storm-swept peak, just a mountain old and quiet, somewhere in the middle of a continent. The kind of mountain that has been standing long enough to forget how it was made. Its slopes are covered in stone and thin soil, and in the right season, a layer of snow so white and still, it looks like the land itself has gone to sleep. Now imagine rain beginning to fall there. Not a storm, not a downpour, just a soft, quiet rain. The kind that arrives in the early morning and settles over everything like a mist. You can barely hear it, just the faintest tapping on rock, the faintest whisper across leaves. A single droplet falls and strikes the surface of a boulder. For a fraction of a second, it holds its shape, a perfect sphere, trembling on gray stone. And then, it breaks apart. It spreads across the surface. It finds a tiny groove in the rock, carved by 1,000 years of water before it, and it begins to move, slowly, barely perceptibly, downhill. This is where rivers begin, not with grandeur, not with force, not with the deep roar of white water, or the wide, silent expanse of a great river curving through a valley. Rivers begin here, in this stillness, with a single drop of water, finding its way downhill. And if you were patient enough to watch, truly patient, the kind of patience that measures itself in decades rather than minutes, you would see something extraordinary happen. You would see that droplet reach the edge of the boulder and fall into a tiny channel between two rocks. You would see it slow down in a small pool, then trickle forward, picking up speed again. On the slope below, you would see it joined by another droplet, and then another, until what started as a trickle becomes a thin thread of water, moving steadily through the soil and stone, and somewhere downstream, farther than you can see, from this mountain, that thread becomes a stream. The stream joins another stream, and another, and somewhere much farther downstream still, in a valley you would need to travel many miles to reach. A river is flowing, wide, calm, carrying the memory of all those tiny droplets on a journey toward the sea. This is the central idea we will follow together, quietly and carefully, over the course of this long exploration. That rivers begin small, almost invisibly, and yet, given enough time measured not in lifetimes, but in millions of years, rivers are among the most powerful sculptors this planet has ever known. They have carved canyons, a mile deep through solid rock. They have carried enough sediment across continents to build entirely new land. At the edge of the sea, they have flattened mountain ranges. They have fed civilizations. They have shaped coastlines. They have redirected the flow of life on this planet in ways both visible and invisible. And they do all of this quietly, patiently, without hurry. The goal of this long, slow journey we are about to take together is simple: to offer simple science explanations for beginners who have perhaps never thought carefully about how a river works, not as scenery, not as a backdrop for human drama, but as an active geological force, one that has been doing its quiet, persistent work long before any human being stood on this earth and looked out across a flowing river and wondered where it came from. How does something as soft as water carve valleys through solid rock? How does a river choose its path? Why do rivers bend? Where does all the sediment go? What happens when a river meets the sea? What happens when a river reaches the end of its life? These are the questions we will answer together, step by step, the way water moves, not in a rush, but steadily, following the natural slope of things, finding the path of least resistance, and arriving at the sea in its own time. You do not need a background in science to follow this. You do not need to know anything about geology or hydrology or geomorphology. Everything we encounter Along the way, will be explained, slowly and clearly, in plain language, with images you can see clearly in your mind, even if you are somewhere, quiet and still, right now. So let the mountain be there, in the early morning rain. Let the droplets fall. Let them trickle down, through stone and soil, and find their way into something larger than themselves. We're going to follow the water. Before we can follow the water, we need to understand what a river actually is. And this is a surprisingly interesting question to sit with for a moment, because most of us have grown up with an intuitive sense of what a river looks like, without ever stopping to think about what it fundamentally is. A river, at its most essential, is a natural channel through which water flows across the surface of the land. That much seems obvious, but the scientific definition goes a little deeper than that. A river is a flowing body of water that moves in a definite channel, shaped by the land it crosses, and over time, by the water itself. And that carries water from higher ground to lower ground, eventually delivering it to another body of water, a lake, another river, or the sea. What makes something a river, rather than just a trickle, or a stream, or a creek? The honest answer is that there is no perfectly sharp line between them. A stream becomes a river by growing larger, by carrying more water, by deepening and widening its channel. But the categories, stream, creek, brook, river, are human ways of organizing what is really a continuous spectrum, a flowing system that changes gradually from tiny to enormous. Let us build this understanding from the ground up. When rain falls on a landscape, or when snow melts on a mountainside, the water has to go somewhere. Some of it soaks into the soil. Some of it evaporates back into the air almost immediately. But a portion of it, the portion that falls faster than the soil can absorb, or that falls on rock, or compacted earth, or frozen ground, flows across the surface. This surface flow is called runoff. It is the origin of rivers. Runoff, at first, is sheet flow, a thin layer of water spreading across the ground, moving slowly downhill under the influence of gravity. But land surfaces are never perfectly smooth. There are tiny ridges and grooves and channels worn into the earth. Runoff naturally concentrates in those low points and moves through them faster, while the higher ground drains into them over time, and sometimes within a single rainstorm. These concentrated flows cut tiny channels into the soil. Those channels become rills. Rills join together and become streams, and streams join together and become rivers. This process of water gathering from a wide area and concentrating into a single channel has a formal name. In hydrology, the science of water, it is called drainage, and the area of land that drains into a particular river is called a drainage basin or a watershed. Think of a watershed like a bowl. The rim of the bowl is the high ground, the mountains, the ridges, the hilltops. Everything inside the bowl tilts toward the center. Any rain that falls inside the bowl will eventually make its way either across the surface or through the ground toward the lowest point. That lowest point is the river. Watersheds are beautifully organized systems. Large rivers have large watersheds, sometimes spanning entire continents. The Amazon River, for example, drains a watershed covering roughly 7 million square kilometers, nearly the entire South American landmass. Above the Andes, every drop of rain that falls within that vast bowl, eventually makes its way through hundreds of smaller streams and rivers into the Amazon and out to the Atlantic Ocean. Within any watershed, water moves through a network of channels, all connected, all flowing downhill. The smaller channels that feed into a larger one are called tributaries. A tributary is simply a stream or smaller river that flows into a bigger one. The main channel that all these tributaries eventually feed into is called the trunk stream or the main stem. Together, the main stem and all its tributaries form what hydrologists call a river system or a drainage network. These networks have a natural structure that scientists have spent a great deal of time studying. If you were to look at a drainage network from the air or trace it on a map, you would notice something remarkable. It looks like a tree. The main river is the trunk. The tributaries are the large branches, and the smaller streams feeding those tributaries are the smaller branches, getting thinner and more numerous as you move toward the edges of the watershed. The very smallest streams, the ones that only flow during and after rain, and that have no permanent water, are like the finest twigs at the outer edge of the tree. This branching pattern is not random. It is a natural consequence of gravity and erosion working together. On a landscape, water always finds the most efficient path downhill. Over time, that process of finding the path of least resistance carves out a drainage network that maximizes the area from which water is collected and minimizes the energy required to move it to the outlet. Now, water in a river does not always flow in one clean, uniform sheet. Real rivers are turbulent, complex, three-dimensional systems. Water moves faster in some parts of the channel and slower in others. It moves faster in the center and slower near the edges, where friction from the banks and the riverbed slows it down. It moves faster on the surface and slower near the bottom. Again, because of friction, these differences in speed across the cross-section of a river are important. They influence how the river shapes its channel, how it carries sediment, and how it erodes the land. Water flowing in a river also carries energy. This energy comes from the height of the water relative to sea level, what scientists call potential energy, and it is converted into kinetic energy, the energy of motion as water flows downhill. A steep river flowing rapidly carries a great deal of energy. A flat, slow river carries less. The energy of a river determines what it can do, how much sediment it can carry, how fast it can erode rock, how quickly it can change its channel. There is one more concept worth introducing here before we move on, and it is the concept of a river's discharge. Discharge is simply the volume of water flowing past a given point in the river per unit of time. It is usually measured in cubic meters per second, or in some countries, cubic feet per second. A small stream might have a discharge of less than 1 cubic meter per second. A large river, like the Mississippi, might discharge several thousand cubic meters per second. The Amazon, at peak flow, can discharge more than 200,000 cubic meters per second, more water than the next 10 largest rivers in the world combined. Discharge changes constantly with the seasons, with rainfall, with snowmelt in the mountains, upstream understanding discharge is fundamental to understanding how rivers behave, how they flood, and how they shape the land around them. So, a river is a flowing body of water moving through a channel fed by tributaries, draining a watershed, shaped by gravity and erosion, carrying energy and sediment, and changing constantly with the seasons and with time. It is, in every sense, a living system, not biologically alive, but dynamically responsive, always adjusting, always moving, always working. That is what a river is. Now, let us think about where the water comes from. Water is ancient. The water that fills the world's rivers today is the same water that has been cycling through this planet for billions of years. A molecule of water in the Amazon River might have been locked inside a glacier 10,000 years ago. Before that, it might have rained down into an ancient sea. Before that, it might have been part of a cloud drifting over a landmass that no longer exists. Water does not arrive on Earth and stay put. It moves endlessly through a cycle that has no beginning and no end. This cycle, the movement of water through the atmosphere, across the land surface, through the ground, and back again, is called the hydrologic cycle, or the water cycle. It is one of the most important processes on this planet, and rivers are one of its most essential pathways. Let us walk through the cycle together, slowly, following a parcel of water through its journey. Begin at the ocean, not a specific ocean, just the concept, a vast body of water covering most of the planet's surface. The ocean is warm at the surface, especially in the tropics, and the sun strikes it continuously during daylight hours. That solar energy is absorbed by the water and causes individual water molecules at the surface to break free of the liquid and rise into the air as water vapor. This process is called evaporation. Evaporation happens constantly from every wet surface on Earth. The ocean is the largest single source. It contributes the majority of the water vapor in the atmosphere. But lakes, rivers, wetlands, and even moist soil all contribute as well. Water vapor rises into the atmosphere, carried upward by warm air currents, and mixed through the lower layers of the sky. As water vapor rises, it moves into cooler air. Cool air cannot hold as much water vapor as warm air. When air cools enough, or when it mixes with enough colder air, the water vapor begins to condense back into tiny, liquid droplets. These droplets gather around microscopic particles in the atmosphere, dust, sea salt, smoke, and form clouds. This process is called condensation. Clouds are enormous collections of these tiny droplets. A single cumulus cloud might contain hundreds of tons of water, all of it suspended in the air, in droplets so small that they fall through the air more slowly than the air currents carry them upward. But as clouds grow, droplets collide and combine, growing larger and heavier. Eventually, they become heavy enough to overcome the upward currents and fall. This is precipitation. Rain, snow, sleet, hail. The form it takes depends on the temperature of the air through which it falls. In mountain regions, much of the winter precipitation falls as snow. This snow accumulates over months, compressed by its own weight into dense layers. Snowpack, as it is called, is one of the most important forms of water storage in the water cycle. In many parts of the world, The snowpack, that builds through winter, releases slowly through spring and summer as temperatures rise, feeding rivers with a steady supply of meltwater long after the winter storms have ended. When precipitation reaches the ground, it faces several possible fates. Some of it evaporates back into the air almost immediately, especially in dry or hot climates. Some of it is taken up by plants through their roots and released back into the atmosphere through their leaves, a process called transpiration. Together, evaporation and transpiration form what scientists call evapotranspiration, and in a healthy, vegetated landscape, this process returns a significant portion of incoming precipitation directly back to the atmosphere. Some precipitation infiltrates into the soil and percolates downward through the ground. This groundwater moves slowly through porous rock and sediment, sometimes taking years or decades to travel from where it entered the ground to where it eventually emerges again. Groundwater is a crucial component of the water cycle. It stores water over long timescales and slowly releases it into rivers, through springs, and through the riverbed itself. In many rivers, particularly during dry seasons, groundwater discharge is what keeps the river flowing when surface runoff has all but stopped. And then there is runoff, the water that flows across the surface of the ground, gathering into channels, building from trickles into streams, and streams into rivers. This surface runoff is the most visible part of the water cycle. It is the water that feeds rivers most directly, and it is the water that moves most quickly through the landscape. A river, then, is one of the primary pathways by which water moves from higher ground, where precipitation first falls, to the sea, where it will evaporate and begin the cycle again. Rivers are not the storage tanks of the water cycle. They are the conveyor belts, the highways, the moving channels through which water transits a landscape on its way from sky to sea. This perspective changes how we see rivers. We tend to think of rivers as fixed features of the landscape, as permanent lines on a map, as landmarks that define the edges of cities and countries. But from the perspective of the water cycle, a river is a temporary pathway. The water passing through it right now was somewhere else a week ago and will be somewhere else again a week from now. The channel is relatively permanent. The water is always passing through. There is something calming about that idea. Water is always moving. It is never truly still, not for long. Even deep groundwater, which might spend 1,000 years slowly filtering through rock, is moving. Even glacial ice, moving perhaps a meter a year, is moving. Everything is in transit. Everything is part of a continuous journey. Rivers are simply the fastest, most visible part of that journey. The moments in the water cycle where movement becomes unmistakably clear. The water in a river channel at any given moment might have arrived there from rain that fell last week just upstream, or it might have arrived as snowmelt that has been filtering slowly through the soil for months, or it might have come up from a spring fed by groundwater that infiltrated the earth years ago, or even decades ago. Rivers are fed by many sources simultaneously and at different times of year. Different sources dominate. In spring, snowmelt typically dominates in mountain-fed rivers. causing the dramatic, seasonal floods and high flows that characterize rivers in temperate and high-latitude regions. In the tropics, where there is no snowpack, river flows are driven more directly by rainfall patterns. Rivers in monsoon climates across South Asia, West Africa, and Southeast Asia experience enormous swings in flow between the wet and dry seasons as the monsoon rains flood the rivers and then retreat, leaving them lower and quieter. These seasonal patterns are not just curiosities, they shape the ecosystems that depend on rivers. They determine when fish migrate, they determine when floodplains are inundated, and when they dry out, they determine when sediment is deposited and when it is eroded. The pulse of a river through the seasons is a fundamental rhythm of the natural world, one we will return to many times as our journey downstream continues. For now, let the cycle complete itself. In your mind, rain falling on a mountain, water gathering and flowing downhill, a river carrying it toward the sea, evaporation lifting it back into the sky, clouds forming, rain falling on a mountain, again and again, without end. We return now to the mountain because this is where rivers are born. Not all rivers begin in mountains, of course. Some begin in flat landscapes, rising slowly from wetlands or from springs that emerge quietly from the ground. But the most powerful rivers, the ones that carve the deepest canyons, that carry the most sediment, that most visibly reshape the surface of the earth, these rivers begin in mountains. And they begin with urgency. A mountain stream is a different creature from the wide, slow rivers of the lowlands. Everything about it speaks of energy and youth. The water is cold, often just above freezing, especially in the upper reaches, where it emerges from snowmelt or glacial runoff. It moves quickly, sometimes very quickly, leaping over boulders and cascading down steep slopes in falls and rapids. It is clear, or nearly clear, because it has not yet had time to pick up much sediment. The streambed is rocky boulders and cobbles and gravel, rounded by the water's force, arranged by the current into patterns that shift and rearrange with every major storm. The steepness of a mountain stream is the key to understanding its character. Steepness, in hydrology, is referred to as gradient, the drop in elevation per unit of horizontal distance. A steep stream loses a great deal of elevation over a short distance. A gentle river loses very little. The gradient of a stream determines how much energy the water carries as it flows. And that energy determines everything. How fast the water moves, how much material it can carry, how effectively it can erode the rock beneath it. In the upper reaches of a river, gradients are often dramatic. A mountain stream might drop hundreds of meters over just a few kilometers. In some glaciated mountain ranges, the gradients are even more extreme, with water cascading nearly vertically down cliff faces before gathering in valleys below. This is what creates waterfalls, points where the stream bed suddenly drops away, where the gradient becomes momentarily vertical, and where the full energy of the water is expressed in free fall. But rivers do not begin only from rainfall. In many parts of the world, a river's life begins in ice. Glaciers, masses of compacted snow and ice that form in mountain ranges and polar regions, where more snow falls each year than melts, are among the most significant sources of river water on Earth. A glacier moves slowly under its own weight, creeping downhill at speeds ranging from centimeters to meters per day. As it moves, it grinds away at the bedrock beneath it with enormous force, carving the characteristic U-shaped valleys that distinguish glacially carved landscapes from water-carved ones. At its lower edges, where temperatures are warmer, the glacier melts. The meltwater flows away in streams that can be turbid with fine glacial sediment. Rock flour, it is sometimes called, ground to a fine powder by the glacier's slow, grinding advance. Research suggests that glaciers worldwide store a substantial fraction of the Earth's fresh water. Water that has been accumulating in ice for thousands of years. Rivers fed by glacial melt have flow patterns that differ from rain-fed rivers. They tend to be coldest and clearest early in the melt season, and murkiest and highest in late summer, when the maximum amount of melting is occurring. Many major river systems, including the Indus, the Ganges, the Mekong, and portions of the Amazon, receive substantial glacial meltwater contributions that moderate their flow and keep them running through the dry season. Springs are another source of mountain rivers. A spring is a place where groundwater emerges naturally at the surface, typically where a layer of permeable rock meets an impermeable layer, and water is forced to the surface. Springs can emerge from the base of cliffs, from valley floors, from the sides of hills. Some springs are tiny, barely noticeable seeps. Others are large enough to form the visible source of a significant river. Springs tend to produce water of remarkably consistent temperature and chemistry because the water has been slowly filtering through rock and acquiring minerals along the way. Spring-fed rivers tend to have more stable flows than rain-fed rivers because groundwater responds to rainfall on longer timescales, filtering slowly through rock rather than running off immediately across the surface. As we move a little downstream from the mountain headwaters, the stream begins to change. The gradient decreases slightly, the channel widens, the water slows not much, but noticeably. The streambed transitions from the chaotic mix of boulders and large cobbles of the high mountain to finer material, smaller cobbles, then gravel, then a mixture of gravel and sand. In the transitional zone between mountain and valley, this transition zone, where the mountain stream begins to behave a little more like a lowland river, is one of the most ecologically rich parts of any river system. The combination of cold, well-oxygenated water, complex channel structure, and diverse substrate makes these reaches highly productive habitats. Many fish species that require cool, clear water, trout, salmon, are characteristic of these transition zones. But what is happening to the landscape here? What is the mountain stream actually doing, beyond simply moving water from high ground to lower ground? The answer is simple. It is working. It is eroding. It is carving. It is slowly, persistently reshaping the surface of the earth. The energy of a mountain stream is not wasted. It is invested. Every bit of kinetic energy that the water carries as it rushes downstream is applied to the task of moving sediment and eroding rock. Young rivers in steep mountain terrain are actively cutting downward into the bedrock, a process called incision. The river cuts a V-shaped valley into the mountainside, steep-walled and narrow at the top of the system, widening gradually as it moves downstream. The deepening of a river valley is not just a geological curiosity, it is one of the fundamental processes by which the surface of the earth is lowered over time. Mountains that were once high are gradually being worn down by the rivers that drain them, grain by grain, boulder by boulder, over timescales of millions of years. The material removed from the mountains is carried downstream and deposited somewhere else, in valleys, in floodplains, at river mouths, on the floors of the sea. This is the great work of rivers, not dramatic, not sudden, but persistent, beyond any human frame of reference. The word erosion might call to mind something dramatic, a rockslide, a cliff crumbling into the sea, a riverbank collapsing in a flood. These things do happen, and they are part of erosion. But most erosion is quiet. Most of it happens at scales too small to see in a single lifetime. Most of it is the accumulated result of countless small events. individual grains of sand being lifted by the current, individual rock surfaces being abraded by moving water, happening continuously over vast stretches of geological time. To understand how rivers erode, we need to think about what moving water actually does. When it comes in contact with rock, the first and most straightforward mechanism is hydraulic action. Water flowing over a surface exerts pressure on that surface. In fast-moving water, this pressure can be substantial. When water rushes into a crack in rock, it compresses the air in the crack and exerts enormous force on the crack walls. Over time, this repeated pressurization and depressurization can wedge the crack wider, loosening blocks of rock that are then carried away by the current. In waterfalls, the plunge pool at the base of the fall is carved primarily by hydraulic action. The sheer force of the falling water, driving rock fragments into the pool floor and hammering away at the bedrock. The second mechanism is abrasion. This is perhaps the most continuously effective form of river erosion. Abrasion occurs when particles carried by the river, sand grains, pebbles, cobbles, are dragged or bounced along the riverbed and banks, grinding away at the surface. Like sandpaper, harder particles grind softer rock. Larger particles grind more effectively than smaller ones. A river, carrying coarse sediment through a valley of softer rock, can abrade its bed at measurable rates, over human timescales. If you have ever held a river-worn pebble, smooth, rounded, fitting perfectly in the palm of your hand, you have held the evidence of abrasion at work. That pebble was not always smooth. It began as an angular fragment, broken from bedrock by some upstream disturbance. As the river carried it downstream, it tumbled and bounced against other pebbles and against the stream bed, and every collision knocked off a tiny chip, rounded an edge, smoothed a surface. The farther a pebble has traveled, the rounder and smoother it tends to become. Scientists can actually estimate how far a pebble has traveled by looking at its degree of rounding, a useful piece of detective work in understanding the history of a river's sediment. The third mechanism is dissolution, sometimes called corrosion. This is a chemical process rather than a physical one. Water is a remarkably good solvent. It does not simply flow over rock. It reacts with it, rainwater, as it falls through the atmosphere and then through the soil, absorbs carbon dioxide and becomes slightly acidic. This weak carbonic acid is capable of dissolving certain types of rock, particularly limestone and other carbonate rocks. Over thousands of years, slightly acidic river water can dissolve enormous quantities of rock, carrying the dissolved minerals away, invisibly in solution. The calcium and magnesium and other minerals that rivers carry dissolved in their water are evidence of this continuous chemical erosion happening somewhere upstream. These three mechanisms, hydraulic action, abrasion, and dissolution, work together, often simultaneously, to erode rock and sediment and carry it downstream, but they do not work equally in all rivers. The rate of erosion in any particular river depends on several factors: the speed of the water, the hardness of the underlying rock, the size and abundance of the sediment the river carries, and the volume of water flowing through the system. Fast rivers erode faster. Rivers carrying coarse, hard sediment abrade their beds more effectively. Rivers flowing over soft rock cut through it more quickly than rivers over hard crystalline rock. These factors combine to produce the enormous variety in erosional landscapes that rivers have carved across the Earth's surface. Consider the Grand Canyon. It is perhaps the most famous example of river erosion visible on Earth. The Colorado River has been cutting through the Colorado Plateau for approximately 5 to 6 million years, according to current scientific evidence. Though the geological story is complex, and research continues to refine this understanding. The result is a canyon roughly 450 kilometers long, up to 29 kilometers wide, and reaching depths of over 1,800 meters. Through that depth, the river has exposed rock layers that record nearly 2 billion years of geological history, an accidental archive of Earth's past. Written in stone, the Grand Canyon impresses us with its scale, but from the perspective of river erosion, it is simply an extreme version of what rivers do everywhere, all the time. Every river valley is a record of erosion. Every V-shaped gorge cut into mountain rock is evidence of a stream that has been patiently cutting downward through the landscape. Even the shallow valley of a small, gentle stream is a product of erosion accumulated over thousands or tens of thousands of years. Rivers also erode laterally, sideways, not just downward, as we will explore later. When rivers develop bends and curves, the outer banks of those curves are subject to intense erosion, while the inner banks receive deposited sediment. Over time, this lateral erosion causes rivers to migrate across their valleys, widening them far beyond what downward cutting alone would produce. And rivers erode not just the rock beneath them, but the land around them. The valley walls of a river canyon are subject to mass wasting, the slow or sudden downslope movement of rock and soil under the influence of gravity, rockfalls, landslides, and the slow creep of soil all contribute material to the river, which then carries it downstream. The river is the engine at the center of a much larger erosional system that involves the entire surrounding landscape. The result of all this erosion over geological timescales is the lowering of the land surface. This is a concept that can be difficult to grasp intuitively because we tend to think of landscapes as permanent, but nothing about a landscape is permanent on geological timescales. The Himalayas are being uplifted by tectonic forces at the same time that rivers are eroding them. The net result at any given time depends on the balance between these two processes: uplift building the mountains, rivers tearing them back down. Research suggests that in actively uplifting mountain ranges, erosion and uplift can approach a rough balance, maintaining the height of the range while continuously recycling material from the mountains to the lowlands and the sea. Erosion, then, is not destruction, it is transformation. The material removed from mountains is not lost, it is transported, deposited, and used to build new landforms elsewhere. Landforms that we will encounter as our journey downstream continues. A river is not just a body of water, it is also always a carrier of material. Every flowing river transports sediment, particles of rock and mineral matter that have been eroded from the landscape upstream and are being moved, grain by grain, particle by particle, toward the sea. Understanding sediment is essential to understanding how rivers work, how they shape landscapes, and how they support the ecosystems that depend on them. Sediment comes in many sizes, and scientists use a fairly precise system to classify it. At the coarsest end are boulders and cobbles, large rocks that can only be moved by very powerful, fast-moving water. Below that are pebbles and gravel, fist-sized to thumbnail-sized fragments. Then comes sand, particles between about 0.06 and 2 millimeters in diameter, the kind that shifts underfoot on a riverbank or a beach. Below sand is silt, particles too fine to feel individually between your fingers, which gives riverbeds and floodplains a silky texture when wet. And finally, at the finest end is clay, particles so tiny that they can remain suspended in water for days or weeks, and that give turbid rivers their characteristic murky brown appearance. Different rivers carry different mixes of sediment depending on the rock types in their watersheds, the gradient of the channel, and the volume of water flowing through the system. A steep, fast mountain stream typically carries coarser material, gravel, pebbles, even boulders during major floods. A slow, flat river crossing a wide plain typically carries finer material, sand, silt, and clay. Rivers that transition from steep mountains to flat plains, which is most of the world's major rivers, carry coarser material in their upper reaches and progressively finer material as they move downstream and slow down. How does a river actually move sediment? There are several distinct mechanisms, and they operate at different scales. The coarsest material, boulders, large cobbles, moves only during major floods, when the river's velocity and force are at their maximum. For most of the year, this material simply rests on the streambed. Only during periods of very high flow does the river generate enough force to dislodge and move these large fragments. Even then, they may move only a short distance before the water slows slightly and they settle again. This intermittent, infrequent movement of coarse material is sometimes called competence-limited transport. The river can only move material up to a certain size, determined by how fast the water is moving. Slightly finer material, gravel and sand, moves more frequently, and by a process called bedload transport. Bedload is the material that moves along the bottom of the channel, rolling, sliding, and bouncing downstream. You can sometimes see and hear bedload movement in shallow, fast-moving streams, a grinding, clicking sound of pebbles being rolled along the streambed by the current. A river in bedload transport is doing visible, audible work. Each pebble being rolled downstream is contributing to the slow lowering of the landscape. Finer material, sand, silt, and clay, can be lifted entirely off the streambed and carried suspended in the water column. This is called suspended load, and it is responsible for the murky brown appearance of rivers after rainstorms. When you see a river running brown and turbid after heavy rain, what you are seeing is an enormous quantity of fine sediment that has been washed from the surrounding landscape and lifted into suspension by the turbulent, fast-moving water. Rivers in flood can carry astonishing quantities of suspended sediment. Research has shown that a river in full flood can transport in a single day more sediment than it would carry in an entire ordinary year. Finally, rivers also carry material in solution, minerals dissolved from rock by the chemical weathering processes we described earlier. This dissolved load is invisible. It does not make the water look murky, but it is substantial. Much of the calcium, magnesium, sodium, and potassium that ends up in the ocean arrives there, dissolved in river water, having been extracted from rocks through millions of years of slow chemical weathering. The total amount of material a river carries, its bedload, suspended load, and dissolved load combined, is called its sediment load. This varies enormously from river to river. Steep rivers in active mountain ranges, carrying easily eroded rock types, can have enormous sediment loads. The Yellow River, for example, is sometimes described as carrying more sediment per unit volume of water than almost any other major river in the world, due to the highly erodible, loess soils of its watershed. Rivers crossing older, flatter landscapes with harder rock types and well-vegetated surfaces may carry much less sediment. What happens to all this sediment? Where does it go? The answer depends on what happens to the river as it moves downstream. When a river slows down, because the gradient decreases, because the channel widens, because the river enters a lake, a reservoir, or a broad valley, it loses energy. And when it loses energy, it begins to deposit sediment. The coarsest material is deposited first, near the upper end of the zone, where the river begins to slow. Finer material travels farther before settling. The finest silt and clay may remain in suspension for hundreds of kilometers before finally settling in the quiet water near the river's mouth or in the sea beyond it. This process of deposition is the other half of the story of rivers. Erosion removes material, transport carries it, deposition builds new landforms. From it, the floodplains, alluvial fans, and deltas that we will encounter later on our journey are all built from deposited sediment, material that was once part of a mountain or a hillside, carried downstream by patient rivers and laid down in a new place to form new land. The sediment cycle is one of the great continuous processes of this planet. Material is eroded from mountains, transported by rivers, deposited in lowlands and seas, compressed over millions of years into new rock, and then uplifted by tectonic forces to form new mountains, which are then eroded again by new rivers. This cycle of erosion, transport, deposition, lithification, and uplift has been running for billions of years, and rivers are its essential conveyor. Ask someone to draw a river, and they will almost certainly draw it with curves. That intuition is correct, given enough space and a gentle enough gradient. Rivers bend, they curve, they wind back and forth across their valleys in graceful sweeping loops that from the air look almost deliberate, as if the river were taking a leisurely route rather than the direct one. These curves are called meanders. The word comes from the Meanders River in western Turkey, known in antiquity as the meander, which winds so extravagantly across its valley that the ancient Greeks used it as a byword for any winding, twisting path. 2,500 years later, scientists still use that word to describe the curves in rivers around the world. Meanders are not random. They are the product of well-understood physical processes, and understanding them reveals something fundamental about how rivers behave when they have the space and the freedom to do so. Begin with a river flowing across a flat, broad valley, a mature lowland river, not a steep mountain stream. The river has a gentle gradient, a wide floodplain, and fine, easily eroded banks. Even in a perfectly straight channel, the flow of water is not uniform. There are always slight irregularities, small differences in the roughness of the channel walls, tiny bends introduced by the deposition of a single large piece of sediment. These slight irregularities cause the thread of fastest moving water, which scientists call the Talveg, to wander slightly from side to side. As the Talveg moves toward one bank, it brings the fastest moving water closer to that bank. Fast-moving water erodes. The bank begins to be cut away, imperceptibly at first, then more noticeably. As that bank retreats, the channel develops a slight bend. The water is now flowing in a curve rather than a straight line. And here, something interesting happens. When water flows around a curve, centrifugal forces push the water toward the outer edge of the bend. The water surface is actually slightly higher on the outside of a meander curve than on the inside. This means that water flows not just downstream, but also at the bottom of the channel, inward across the bend, from the outer bank toward the inner bank. This spiral flow pattern, called helical flow or secondary circulation, has a crucial effect on sediment at the outer bank, where the water is fastest and the force of the flow is greatest. The river erodes. The bank is cut away, undercut, and collapses into the channel. chunks of bank material, fall into the water and are carried away. As sediment, this erosion continues, and the outer bank retreats, progressively outward, making the bend wider and more pronounced. At the inner bank, the opposite happens. The helical flow carries sediment inward and deposits it on the inside of the curve, where the water moves more slowly. Over time, a wedge-shaped deposit of sand and gravel builds up on the inner side of every meander, a feature called a point bar. You have probably seen point bars without knowing their name. They are the gentle, sandy or gravelly beaches that form on the insides of river bends where the water is shallow and calm. So every meander bend has two sides working in opposite directions. The outer bank eroding and retreating, the inner bank building and advancing through deposition. The result is that the bend does not stay in place. It migrates. The outer bank retreats, the inner bank advances, and the whole curve moves across the valley floor, usually in the downstream direction, but sometimes also laterally, sweeping from side to side across the floodplain. Over time, meanders grow larger and more sinuous. The curves become more and more pronounced, until in some rivers, they form almost complete loops. The neck of the loop becoming very narrow, as the surrounding curve has grown so large that the river has almost come full circle. At some point, during a flood, or after years of slow erosion, the river cuts through the narrow neck and takes a more direct route downstream. The abandoned loop is left behind, a curved lake, cut off from the main river, slowly filling with sediment. These abandoned meanders are called oxbow lakes because their shape resembles the U-shaped wooden yoke used to harness oxen. In earlier centuries, oxbow lakes are characteristic features of mature river floodplains. They dot the landscape like parentheses, gentle reminders of where the river used to flow. Before it took a shortcut, they gradually fill with sediment and organic matter, transitioning over centuries from open water to swamp to wetland to meadow. Each one is a small archive of the river's history, a ghost of an old meander preserved in the landscape. From the air, a mature river system with fully developed meanders is one of the most visually striking landscapes on Earth. The wide flat valley is crossed and recrossed by the gleaming curves of the river, bordered by the pale outlines of old meanders and oxbow lakes. The snake-like path of the river seems almost impossibly extravagant. Why does it not just go straight? But as we have seen, straight is not what rivers naturally do. Meanders are the river's natural state when it has the freedom and the energy to explore. The degree of meandering in a river can be measured scientifically. A perfectly straight river would have a sinuosity of 1.0. As a river becomes more curved, its sinuosity increases. The actual length of the river, divided by the straight line distance from source to mouth. Some highly meandering rivers have sinuosity values of 3 or 4 or more, meaning the river travels 3 or 4 times farther than the straight line distance through the valley. The lower Mississippi River, for example, has historically been one of the most sinuous rivers in North America, with loops and curves that wind extravagantly across its broad floodplain. Meanders also have a characteristic scale that is proportional to the size of the river. Scientists have found that the wavelength of a meander, the distance from one loop to the next, is typically about 10 to 14 times the width of the river channel. A small stream, a meter wide, will develop meanders with wavelengths of 10 to 14 meters. A large river, a kilometer wide, will develop meanders with wavelengths of 10 to 14 kilometers. This self-similar relationship suggests that meanders arise from fundamental physical principles governing how water flows in channels rather than from random chance or local geography. It is one of many examples in river science of patterns that repeat at different scales, a characteristic of systems governed by consistent physical laws, operating on variable amounts of material downstream from the mountains. In the broad lowlands, where rivers flow and spread, there is a landscape that rivers have been building and rebuilding for as long as they have been flowing. It is the floodplain, and understanding it requires letting go of the idea that floods are exceptional events. For floodplains, floods are the norm. They are the design. A floodplain is the flat land bordering a river that is periodically covered with water when the river overflows its banks. That definition makes floods sound like disturbances, intrusions of water into a landscape that normally exists without it. But that framing gets things backwards. The floodplain was built by floods. It is maintained by floods. It is ecologically adapted to floods. The river and its floodplain are a single, integrated system, and the periodic overflow of the river into the surrounding land is not an accident. It is a fundamental part of how the system works. Let us think about why rivers flood in the first place. A river channel is shaped over time to carry the river's average or typical flow during normal conditions. The water stays within the channel, but rivers do not flow at a constant rate. Their discharge varies with rainfall and snowmelt, sometimes enormously. A river that normally flows at, say, 500 cubic meters per second might, during a major storm, receive 10 times that much water from its watershed. The channel, shaped to handle 500 cubic meters per second, cannot contain 5,000. The water rises above the bankful stage, as hydrologists call it, and spreads out across the floodplain. This overflow is not violent. Most of the time, in many rivers, a flood is more of a slow, broad spreading of water than a sudden surge. The water rises gradually, extending across the flat land bordering the channel, covering fields and marshes and low-lying woodland. It may stay for days or weeks before the upstream peak passes and the water slowly recedes. When it recedes, it leaves behind a thin layer of sediment, the finest particles, silt and clay, which settled out of the water during the quiet period of inundation. It is this layer-by-layer deposition of fine sediment that built the floodplain. In the first place, every flood adds a little material over hundreds and thousands of years. The accumulation is significant. Floodplains can be meters thick in accumulated sediment, rich, fine-grained material with an exceptional ability to hold water and nutrients. This is why floodplain soils are so extraordinarily fertile. They are, in essence, continuously renewed by the river. Each flood brings not just water, but also nutrients, organic matter, dissolved minerals, fine particles from the watershed upstream. When the water recedes, those nutrients are left behind in the soil. Ancient civilizations understood this intuitively, even without the formal science. The annual flood of the Nile, which inundated the agricultural lands of the Nile Valley each summer, was the foundation of Egyptian civilization. It was not a catastrophe, it was a gift. The thick layer of dark, rich sediment deposited by the floodwaters renewed the soil every year, making continuous agriculture possible in an otherwise desert environment. The Egyptians called this fertile dark soil Kemet, the black land, to distinguish it from the red, infertile desert soil that surrounded it. The floodplain is also shaped by the river's tendency to move its channel. Over time, meanders migrate. Old channels are abandoned. New ones are cut. Over centuries and millennia, a river might occupy many different positions within its floodplain, leaving a complex stratigraphy, layers of different sediments deposited in different positions of the river channel, buried beneath the flat surface. Drilling into a floodplain is like reading a book of the river's history. There are structures within the floodplain that are particularly interesting. One of the most characteristic is the natural levee, a low ridge of coarser sediment that builds up along the immediate banks of the river. When the river overflows its banks during a flood, the water immediately adjacent to the channel is moving relatively quickly and carries coarser sediment. As this water spreads across the floodplain and slows, it deposits the coarser particles first near the channel. This repeated deposition of coarser material near the bank builds a low ridge, often just a meter or two high, but enough to keep the river slightly contained during moderate floods and to create a slight elevation difference between the river's edge and the floodplain. Behind it, beyond the natural levee, the floodplain is often slightly lower, a back basin or back swamp where water collects and drains slowly during floods. These low-lying areas are often wetlands, maintaining some level of standing water or saturated soil. Much of the year, they are among the most ecologically productive parts of the floodplain, supporting dense vegetation and diverse animal communities. Floodplains also feature scroll bars, the curved ridges and swales left by the migration of meander bends across the valley floor. Each curved ridge marks the position of a former point bar deposited on the inside of a meander. As the meander migrated, it left a series of these scroll-like ridges, visible from the air, as a series of nested curves. In the floodplain surface, between the ridges, are swales, slight depressions that collect water and remain wet or marshy. The entire floodplain, seen from the air, is a record of the river's movement, a landscape written in subtle topography, each feature telling part of the story of where the river has been. From the perspective of ecosystems, the periodic flooding of the floodplain is essential. Many plant species that grow in floodplain forests are specifically adapted to tolerate inundation for weeks at a time. Willows and cottonwoods along North American rivers, for example, have seeds that are released precisely when floods are receding, carried by the water to newly deposited sediment banks, where they germinate quickly before conditions change. The timing of their reproduction is synchronized with the river's flood pulse in a relationship refined over thousands of years of coevolution. Fish, too, depend on the seasonal flooding of the floodplain. When a river floods into a surrounding forest or wetland, it brings fish that spread across the shallow, warm, food-rich flooded areas to feed and spawn. In the Amazon, research has shown that large floodplain forests, agapo and várzea, are critical feeding grounds for dozens of fish species. During the high water season, the fish gorge on fruits, seeds, and invertebrates in the flooded forest, accumulating energy reserves. that sustain them through the dry season. When food is scarce, the floodplain, then, is not merely a place where the river occasionally spills. It is an integral part of the river system, a living, breathing extension of the river that floods and dries and floods again with the seasons, building fertility, supporting biodiversity, and recording the river's long history in its layered sediments and curved landforms. Every river, in the end, meets the sea, or a lake, or another river. But for the rivers that carry sediment to the coast, this final meeting produces one of the most dramatic and ecologically significant landforms on Earth. The delta. A delta is built at the mouth of a river, where the river's velocity drops so suddenly and completely that the sediment it has been carrying can no longer remain suspended or in motion. The river, slowing as it enters the still water of a sea or lake, drops its load. The coarsest material is deposited first. The finer silt and clay settle more slowly, spreading farther out into the receiving body of water. Over time, this accumulated sediment builds new land, extending the coastline outward, filling in the shallow water at the river's mouth with layer upon layer of deposited material. The result is a flat, low-lying, fan-shaped accumulation of sediment at the river's mouth. The delta, the word, was first used by the ancient Greek historian Herodotus to describe the triangular shape of land at the mouth of the Nile River, which from the air resembled the triangular Greek letter delta. Not all deltas are perfectly triangular, as we will see, but the name has stuck. What determines the shape of a delta? It depends on the balance between the sediment brought by the river and the forces acting to redistribute that sediment. Once it is deposited, the three primary external forces are the waves of the receiving sea or lake, the tidal currents moving in and out of the river mouth, with the rise and fall of the sea and the river's own outflow. Different balances of these forces produce different delta shapes, where the river's sediment supply is very high and the waves and tides are relatively weak. Conditions found in enclosed or calm seas. The river dominates. The sediment builds up directly in front of the river mouth, forcing the channel to split and resplit into a network of distributary channels that fan out across the growing delta surface. The result is what geologists call a bird's foot delta, a series of long, narrow lobes of land extending into the sea, separated by the distributary channels between them. The classic example is the delta of the Mississippi River, its elongated lobes extending into the Gulf of Mexico, giving the delta its characteristic shape, which from the air does indeed look somewhat like the outstretched toes of a bird. Where waves are stronger, they rework the deposited sediment as fast as the river delivers it, smoothing the coastline and redistributing material along the shore. The result is a more rounded, arcuate delta, smoother in outline, with fewer protruding lobes. The delta of the Nile River is a well-known example, roughly triangular in outline, with a relatively smooth northern coastline shaped by the waves of the Mediterranean Sea. In areas with strong tides, the ebb and flow of tidal currents dominates, reworking sediment into a series of elongated tidal channels, separated by mudflats. The result is a tide-dominated delta, a complex, branching network of channels with an irregular, fingered shoreline. Most real deltas are influenced by all three forces to varying degrees, and their shapes represent the current balance between them, a balance that can shift as sea level changes, as the river's sediment supply changes, or as climate patterns shift. Deltas are among the most dynamic landscapes on Earth. The distributary channels that cross a delta surface are inherently unstable. A river building a delta eventually develops such a long, inefficient path to the sea through the growing sediment body that it will seize any opportunity to find a shorter route. When a major flood occurs, the river may overtop one of its natural levees and begin flowing through a new, shorter path to the sea. If the new path is significantly more efficient than the old one, the river may progressively shift its main flow to the new channel. The old delta lobe, deprived of its water and sediment supply, begins to sink and erode. The new lobe begins to grow. This process, called delta switching or avulsion, has happened repeatedly in the history of major deltas. The Mississippi River, for example, has switched its main channel several times over the past 5,000 to 7,000 years, building different lobes of the modern delta in succession. Scientists now recognize that the river naturally tends to shift toward the shorter route of the Atchafalaya River, a shift that today is being managed by extensive engineering works. Deltas are more than just landforms. They are among the most biologically productive ecosystems on Earth. The continuous supply of nutrients from the river, the shallow water depths, and the complex habitat structure of channels, mudflats, marshes, and floodplains create conditions that support extraordinary biodiversity. The Great Delta, formed by the Ganges River and the Brahmaputra River, contains the vast mangrove forest known as the Sundarbans, one of the largest mangrove ecosystems in the world, home to Bengal tiger, river dolphins, countless bird species, and some of the most productive coastal fisheries in Asia. The Nile Delta supports agriculture that has fed civilizations for millennia. The marshes of the Mississippi River Delta are critical nursery habitats for fish and shellfish that sustain major commercial fisheries. In the Gulf of Mexico, deltas are also where some of the densest human populations in the world live. The fertility of delta soils, the availability of fresh water, and the access to both river trade and coastal fishing have drawn people to deltas throughout human history. Many of the world's great cities, including Alexandria, Cairo, Kolkata, Dhaka, Ho Chi Minh City, and New Orleans, are built on or near deltas. This makes deltas, with their dynamic, changeable nature, places of great interest to scientists studying how rivers, seas, and human systems interact. Water is life. This is a statement so obvious that it might seem trivial, but when we think carefully about rivers, it becomes genuinely profound. Rivers do not just provide water for living things, they create the very conditions that make complex ecosystems possible. They shape the land, deliver nutrients, maintain gradients of temperature and chemistry, and connect distant parts of the landscape in ways that sustain biodiversity at every scale. Let us move slowly through the river, from upstream to downstream, and consider the life that inhabits each part of it. In the cold, fast-flowing headwater streams of mountain rivers, the environment is demanding The water is well oxygenated. Fast, turbulent water mixes constantly with air, maintaining high oxygen levels, but it is cold, often close to freezing, and the physical forces of fast-moving water over rocky beds make life difficult for anything that cannot hold on or hide. The organisms adapted to this environment tend to be specialized. Aquatic insects, stoneflies, mayflies, caddisflies have evolved life stages that grip the undersides of rocks in the current, feeding on algae and organic matter that drift downstream. These insects, in turn, are the primary food source for fish adapted to cold, fast water. The fish most associated with cold mountain streams are salmonids, a family that includes trout, salmon, and related species. These fish are superbly adapted to their environment, powerful swimmers with streamlined bodies capable of holding position in fast current or leaping obstacles in their path. Many salmon species are anadromous. They hatch in freshwater streams, migrate to the ocean, where they spend their adult lives, and then return to the same freshwater stream where they were born to spawn and die. This extraordinary life cycle connects ocean ecosystems to freshwater ones, and it has cascading effects on the entire watershed. When salmon die, after spawning, their bodies decompose and release nutrients into the stream water and the surrounding forest. Research has found that the nitrogen and carbon in salmon carcasses, which are derived from the ocean during the salmon's years at sea, can be traced into the tissues of streamside trees and plants. Bears, eagles, and other animals carry salmon carcasses away from the stream into the surrounding forest, spreading marine-derived nutrients across a wide area. The salmon, in this sense, are a conveyor of nutrients from the sea to the mountain forest, a biological link in the river system that connects ocean and land, moving downstream into lower gradient rivers with wider valleys and warmer water. The character of the ecosystem changes. The streambed transitions from bare rock to gravel and sand. Aquatic plants can take root in the more stable substrate. Algae grow more abundantly in the slower current. The diversity of invertebrates increases with a greater variety of feeding strategies represented. Fish communities diversify as well, adding species adapted to warmer water and more varied habitats. Bass, pike, catfish, perch, and many others, depending on the continent and the river system. The banks of middle reach rivers are occupied by riparian forests, the distinctive tree and shrub communities that grow along river corridors. Riparian, from the Latin for of the riverbank. These forests are shaped by their proximity to water. They have access to abundant groundwater, even during dry periods, and they must tolerate periodic flooding. In return, they occupy some of the most productive growing sites in the landscape, and they play an essential role in the river ecosystem. The roots of riparian trees stabilize stream banks, reducing erosion. Fallen trees, large woody debris, as ecologists call it, create complex habitat structure in the stream channel, providing refuge for fish and invertebrates and slowing the current in ways that create pools and riffles. The leaf litter from streamside trees falls into the water and becomes the primary food source for many aquatic invertebrates in forested streams. Riparian forests also moderate stream temperature. The shade cast by overhanging trees keeps stream water cooler. In summer, critical for cold water fish, such as trout, which have limited tolerance for warm water. Removing riparian vegetation from a stream can increase summer water temperatures enough to eliminate trout populations. The river also connects distant habitats in ways that are easy to overlook. Wetlands, areas of shallow water, and saturated soil are often located along river corridors, in floodplains, and in back basins, behind natural levees. Wetlands are among the most productive ecosystems on Earth. They serve as nursery habitat for fish that spawn in wetland shallows. They provide feeding and nesting habitat for enormous numbers of waterbirds, herons, egrets, ibis, ducks, geese, wading shorebirds. They filter water by slowing its movement and allowing suspended sediment and nutrients to settle out. They store floodwater, reducing the peaks of downstream floods, and they are among the most carbon-rich ecosystems known. Their waterlogged soils preserve organic matter from decomposing, building up thick layers of peat over thousands of years. In the lower reaches of rivers, as the channel widens and slows and the floodplain broadens, the river ecosystem takes on yet another character. Water clarity decreases as the river carries more suspended sediment. Aquatic vegetation grows in the shallower margins. The river's connection to its floodplain becomes more intimate with seasonal flooding, linking the main channel to oxbow lakes, swamps, and floodplain forests. And finally, at the river's mouth, where freshwater meets the sea, there is the estuary, one of the most productive ecosystems on Earth. An estuary is a body of water where a river mixes with salt water, creating a gradient from fresh to saline. The mixing of fresh and salt water creates complex chemical conditions and typically brings high concentrations of nutrients, the legacy of the entire river system. Concentrating here, at the final stage, estuaries are nursery habitats for an enormous proportion of commercially important marine fish, shrimp, crabs, oysters, clams. Many of the most economically valuable marine organisms spend crucial phases of their life cycles in estuaries, taking advantage of the nutrient richness and the shelter provided by estuarine vegetation. Estuarine wetlands, salt marshes in temperate latitudes, mangroves in the tropics are among the most productive ecosystems per unit area on Earth, and they buffer coastlines from storm waves and erosion. The river system, from headwaters to estuary, is an integrated ecological network, each part connected to every other part by the continuous flow of water, sediment, and nutrients. Life along rivers is not incidental, it is intrinsic. The river does not merely pass through the landscape, it sustains it wherever you find the beginnings of human civilization. The first cities, the first organized agriculture, the first written language, the first complex trade networks. You find rivers. This is not a coincidence. Rivers made these things possible, and understanding why tells us something important about the relationship between human cultures and the natural systems that support them. The earliest settled human communities appear to have developed in regions where rivers provided reliable water for agriculture. The Tigris and Euphrates rivers of modern-day Iraq and Syria gave rise to the civilizations of Mesopotamia, one of the earliest cradles of urban life, writing, and organized governance. The Nile in northeast Africa supported the civilization of ancient Egypt. whose remarkable continuity across 3,000 years was grounded in the fertility of the Nile's annual flood. The Indus River, in what is now Pakistan and northwestern India, supported the Indus Valley Civilization, contemporary with ancient Egypt and Mesopotamia, and notable for its sophisticated urban planning and drainage systems. The Yellow River and the Yangtze in China supported the development of Chinese civilization. In each case, the river provided something essential that dry land alone could not: a reliable, renewable supply of fresh water for crops. Agriculture transforms the relationship between human communities and the land. A farming community needs to stay in one place long enough to plant, tend, and harvest crops. It needs water reliably at the right times of year. Rivers provided both. In semi-arid regions, where rainfall was insufficient or too unpredictable for reliable rain-fed agriculture, rivers made it possible to irrigate cropland by diverting river water into fields through channels and ditches. The earliest irrigation systems are remarkably ancient. Evidence of canal irrigation in Mesopotamia dates back more than 6,000 years. The Egyptians developed intricate systems for managing the Nile's annual flood, channeling water onto fields and then draining it back into the river. In China, extensive canal systems transformed the floodplains of the Yellow River and later the Yangtze into some of the most intensively farmed landscapes in the world. These irrigation systems were among the first large-scale engineering projects in human history, requiring organized labor, planning across multiple seasons, and governance structures capable of coordinating the efforts of large numbers of people. Rivers also served as highways. In a world without roads before the invention of wheeled vehicles, rivers offered a fundamentally easier means of moving heavy goods over long distances. A boat could carry more cargo than a pack animal, required less energy per unit of freight, and could move continuously day and night on a favorable current. Rivers became the arteries of trade connecting interior regions to coastal ports and to each other. The importance of rivers as trade routes shaped the locations of cities. Many of the world's major cities, and particularly the oldest ones, are located at strategic points on rivers, at the confluence of two rivers where trade routes met. At the tidal limit of a river, the farthest point upstream that ocean-going vessels could reach. At natural crossing points where rivers could be forded or bridged. London sits on the Thames at its tidal limit. Paris sits on the Seine at the crossing point where ancient roads converged. Cairo sits on the Nile at the transition from the narrow valley to the broad delta. The geography of rivers shaped the geography of urban civilization. Rivers also provided power, long before the era of steam and electricity. Water mills, in which the force of flowing water is used to turn a wheel that drives machinery, were among the most transformative technologies of the pre-industrial world. Water mills ground grain into flour, drove hammers in metalworking, powered looms in the early textile industry. The rivers of medieval Europe were dotted with mills at almost every suitable location. The Industrial Revolution in Britain began in part in the valleys of fast-flowing rivers in Yorkshire and Lancashire, where the swift currents provided power for the first textile factories. Rivers also carried away waste, a less celebrated but equally important service to human communities. Cities generate enormous quantities of sewage, garbage, and industrial waste. Rivers, with their constant flow, diluted and carried away this waste at least partially. The convenience of rivers as disposal systems encouraged dense settlement along their banks, and eventually created the water quality problems that developed cities have spent the past 2 centuries struggling to address. The relationship between rivers and human civilization is deep, complex, and ongoing. It is a relationship shaped not just by what rivers provide, but by how rivers behave, by their floods and their droughts, their sediment and their course changes, their seasons and their long-term evolution. Human civilizations have adapted to rivers, and have adapted rivers to themselves, in an ongoing negotiation that continues today. The 20th century saw an unprecedented change in the human relationship with rivers. As populations grew, as demand for water, food, and electricity increased, as the tools of engineering became ever more powerful, humans began to modify rivers at a scale that had no precedent in history. The dam is the most visible symbol of this transformation. A dam is a barrier constructed across a river to obstruct the flow of water. Behind the dam, the river backs up into a reservoir, an artificial lake. The water stored in the reservoir can be released in a controlled fashion for irrigation, for drinking water supply, or through turbines to generate hydroelectric power. Dams also reduce downstream flood risk by absorbing excess water during wet periods and releasing it slowly. In terms of sheer engineering scale, some of the world's largest dams are among the most impressive structures ever built. The Three Gorges Dam on the Yangtze River in China, completed in 2006, has a reservoir stretching more than 600 kilometers upstream and generates enormous quantities of electricity. The Hoover Dam on the Colorado River in the United States, completed in 1936, created Lake Mead for many years, the largest artificial reservoir in the world by volume. Thousands of smaller dams exist on rivers around the world, ranging from massive concrete arch structures to modest earthen embankments. The benefits of dams are concrete and significant. They provide reliable water supplies for irrigation, making agriculture possible in regions that would otherwise be too dry. They supply drinking water to cities. They generate hydroelectric power, a source of electricity that emits no greenhouse gases during generation, and that can be quickly adjusted to meet fluctuating demand. And they reduce the risk of catastrophic flooding downstream, protecting lives and infrastructure. But dams also have significant effects on river systems. And understanding these effects requires thinking about rivers as the connected sediment-transporting, ecologically integrated systems we have been describing throughout this journey. The most direct effect is on sediment. A dam traps sediment. The sediment that the river would normally carry downstream accumulates in the reservoir, settling out as the water slows. Over time, reservoirs fill with sediment, a process that reduces their storage capacity and can eventually make them less effective. More importantly, from the river's perspective, the clear water released downstream from a dam is sediment hungry. Because the water has had all its sediment removed by the reservoir, it picks up new sediment from the downstream riverbed and banks with unusual aggressiveness, a process called channel degradation or hungry water erosion. Rivers below large dams often scour their beds deeply, in some cases exposing bedrock that was formerly covered by sediment. This sediment disruption has cascading effects. The floodplains downstream no longer receive the periodic deposits of fine sediment that maintain their fertility. Deltas cut off from their sediment supply no longer grow. In some cases, they begin to shrink. The ongoing subsidence of the delta, driven by the compaction of older sediment, is no longer offset by the deposition of new material. The Nile Delta, for example, has been measurably subsiding and eroding since the construction of the Aswan High Dam in the 1960s, which traps most of the Nile River's sediment in Lake Nasser upstream. Dams also fundamentally alter the flow regime of rivers, the pattern of high and low flows through the year. This has profound consequences for ecosystems that have evolved to respond to the river's natural seasonal rhythm. Fish species that rely on high spring flows to trigger migration and spawning may find that the dam has muted or eliminated the spring flood pulse. Riparian vegetation that relies on seasonal flooding to germinate or to disperse its seeds may be compromised by the more regulated, consistent flows below a dam. The passage of migratory fish is one of the most well-documented effects of dams. Salmon, shad, sturgeon, and other migratory species that move between the ocean and freshwater to spawn are blocked by dam barriers. The effects on salmon populations in the Columbia River system of the Pacific Northwest, for example, have been extensively researched, with evidence that dam construction contributed significantly to the decline of salmon runs that once numbered in the tens of millions. Many modern dams include fish passage structures, fish ladders, and bypass channels designed to allow fish to move past the dam barrier. These structures have variable success, and research continues on how to improve their design and effectiveness. The broader lesson of dams is that rivers are integrated systems, and interrupting one part of the system has effects that ripple throughout. This does not mean dams are unequivocally negative. The water and electricity they provide are genuinely important to human well-being. But it does mean that their design and operation require careful consideration of the full range of effects on river systems and the communities that depend on them. In recent decades, there has been growing scientific and policy interest in dam removal. The deliberate dismantling of aging dams that have reached the end of their operational life and whose costs have come to outweigh their benefits. Research on river recovery following dam removal has shown that rivers can recover their sediment transport, their channel form, and their fish populations relatively quickly once the dam barrier is removed, in some cases within years to decades. These observations have informed a growing understanding of river resilience, the capacity of river systems to recover and reorganize following disturbance. Rivers exist within the broader context of Earth's climate system, and as that system changes, rivers are changing with it. This is a topic that warrants careful, scientifically grounded discussion, one that neither minimizes the changes underway nor overstates them beyond what current evidence supports. The fundamental connection between climate and rivers is through the water cycle. Rainfall patterns determine how much water enters river systems. Temperature determines how much of that water evaporates before reaching rivers, and how much precipitation falls as snow versus rain. The extent and persistence of snowpack, which many rivers depend on for their summer flows, is sensitive to temperature, and sea level, which is the ultimate base level to which rivers flow, is changing as well. Research indicates that patterns of precipitation are shifting in many parts of the world as the climate warms. The general expectation from current climate science is that wet regions will tend to become wetter and dry regions will tend to become drier, though the specific patterns vary enormously by region and season. More precipitation falling as rain rather than snow in mountain regions is expected to alter the timing of river flows, with more water arriving in winter when it falls as rain rather than accumulating as snowpack for gradual release in spring and summer. In regions that rely on glacial meltwater, the high-altitude rivers of Central Asia, the Andes and the Himalayas that feed some of the world's most densely populated regions, current evidence suggests that glaciers are generally losing mass. Research indicates that in the near term, glacial retreat can actually increase meltwater flows as the glacier loses mass. But in the longer term, as glaciers diminish, rivers that depended on them for their dry season flows may experience reduced summer flows. Scientists are actively working to better understand and quantify these changes, and there is genuine uncertainty about the timescales and magnitudes involved. The behavior of extreme events, particularly floods and droughts, is an active area of research in hydrology and climate science. Current evidence suggests that in many regions, the frequency or intensity of extreme rainfall events is increasing with warming temperatures. Warmer air can hold more water vapor, and when storm conditions cause that water vapor to condense and fall, the resulting precipitation can be more intense. More intense rainfall can lead to more rapid runoff and higher peak flows in rivers. This does not mean that all floods are increasing everywhere. The picture is complex, regional, and influenced by many local factors, including land use change. Drought, periods of anomalously low river flow, is another concern in many regions. Extended droughts reduce river flows, concentrate pollutants, increase water temperatures, and stress river ecosystems. Research suggests that in some semi-arid regions, droughts are becoming more frequent or more severe, driven by changing precipitation patterns and by increased evaporation in a warmer atmosphere. It is worth noting with appropriate caution that rivers have always been variable. They have experienced floods and droughts throughout their natural history, long before human influence on the climate system. The question for researchers is whether human-caused warming is changing the frequency, intensity, or duration of these natural extremes in ways that are outside the range of historical variability. This is a question that current science is actively investigating, and the answers are emerging with increasing confidence in some regions and areas, and less certainty in others. What is clear is that rivers respond to climatic changes, and that understanding those responses so that communities and institutions can plan accordingly requires continued investment in monitoring, research, and modeling. Rivers are, in a sense, one of the most sensitive and visible indicators of climate change, integrating signals from across entire watersheds into the single measurable variable of stream flow. Rivers are not static features. They are not born fully formed and then unchanged until some catastrophic event destroys them. They evolve over time, slowly across geological timescales, changing their character, their behavior, and their relationship to the landscape as they age. Understanding this long life cycle of rivers gives us yet another perspective on the patient, persistent nature of flowing water as a geological force. The concept of river maturity is a useful, if simplified, way of thinking about how rivers change over time. A young river, in geological terms, is one that has not yet had enough time to adjust fully to the landscape it flows through. Young rivers tend to be steep, fast, and erosionally active. They cut downward rapidly, carving V-shaped valleys into the rock beneath them. Their channels are relatively straight or only gently curved. They carry coarse sediment. They have high energy and are doing active erosional work. Over time, a young river cuts its valley deeper and deeper. The valley walls are steepened by the downcutting river. Eventually, the valley becomes too steep and begins to slide. Mass wasting delivers more material to the river, and the river carries it away. The valley walls retreat. The valley widens. The gradient of the river decreases as the valley floor lowers and the source of the river's flow shortens. The river begins to lose some of its youthful energy. As the river matures, it begins to develop the features we have described: meanders, floodplains, broader valley floors. The river no longer cuts predominantly downward. It cuts increasingly laterally, widening its valley and building its floodplain. Mature rivers have lower gradients, finer sediment, and more sinuous channels. They are less energetically active than young rivers, but in some ways more geomorphically effective, because they are reshaping a larger area through lateral migration. An old river, in geological terms, flows across a landscape that has been eroded and flattened over millions of years. The relief of the surrounding terrain has been reduced. The river meanders across a wide, flat plain, its gradient barely perceptible. It carries very fine sediment. It is close to what geomorphologists call grade, a condition of approximate equilibrium, where the river's energy is just sufficient to transport the sediment supplied to it. with neither significant erosion nor significant deposition. The classic concept of a river's long-term evolution from youth to maturity to old age was developed by the American geographer William Morris Davis in the late 19th century in what he called the geographical cycle, or cycle of erosion. Davis imagined landscapes beginning with tectonic uplift, creating high, rugged terrain, young, energetic rivers cutting through it, gradually wearing down through maturity, to old age, flat, nearly featureless plains drained by sluggish rivers. Modern geomorphology has refined, and in some cases challenged, Davis's model. Real landscapes rarely follow such a neat, unidirectional progression. Tectonic activity can renew uplift at any stage, rejuvenating a river system that had been aging toward flatness. Climate changes can alter erosion rates, base level changes, changes in the elevation of the ocean or lake into which a river flows, can send a wave of renewed erosion upstream through an entire river system. Rivers are constantly adjusting to multiple changing inputs, and their evolutionary trajectories are more complex than any simple model can capture. Nevertheless, the underlying insight remains valid. Rivers change over time. The landscape you see a river flowing through today is not the landscape that river has always occupied. If you could watch a river in fast forward over millions of years, you would see it cut its valley, widen it, flatten it, migrate across it, and gradually reduce the surrounding terrain to a lowland, drained by gentle wandering streams. And if tectonic forces renewed uplift, you would see the process begin again. A new wave of downcutting, new steep valleys, new energetic rapids, new beginnings. Rivers, like all geological features, have long lives, but those lives have chapters. Let us slow down here for a moment and simply think about what we have been describing. Water is soft. Hold your hand under a tap and feel the water flow over it. There is almost no force there, certainly not enough to carve rock. Yet we have been describing rivers that have cut canyons more than a kilometer deep through solid stone. Rivers that have transported billions of tons of sediment across continents. Rivers that have built deltas the size of entire countries. Rivers that have carved the shapes of mountain ranges and reconstructed coastlines. How do we reconcile these two things? The softness of water and the scale of what rivers have accomplished. The answer is time. And this is perhaps the most important concept to carry with you from everything we have explored today. The quiet power of water is not about force. It is about persistence. It is about the relentless, uninterrupted application of small forces over timescales that dwarf anything we can meaningfully imagine. A river does not carve a canyon in a dramatic moment of geological violence. It carves it grain by grain, stone by stone, over millions of years of continuous flow. Each individual grain of sediment, dragged across the bedrock, scratches it infinitesimally. Each individual water molecule, pressing into a crack in the rock, exerts an infinitesimal force. But multiply those infinitesimals by a number large enough, by millions of years of daily flow, by billions of cubic meters of water, by trillions of individual sediment grains, and you get the Grand Canyon. You get the Yangtze Gorges. You get the great V-shaped valleys of the Alps and the Himalayas. This is the essence of geological time, and rivers are among its clearest teachers. Humans live on timescales of years and decades. We plan for decades at most. We can barely imagine a century, let alone a million years. And yet the processes that shape the Earth's surface operate over timescales that are not just longer than human life, but longer than human civilization, longer than the entire history of our species. The Himalayan rivers, the Indus River, the Ganges River, the Brahmaputra River, have been cutting their valleys for tens of millions of years. keeping pace with the tectonic uplift of the mountain range, as it has been squeezed upward by the collision of tectonic plates. These rivers are not young in any meaningful sense. They are ancient beyond reckoning, and they are still doing their work, still cutting, still transporting, still depositing, without hurry, without urgency, simply persisting. There is something worth noticing in this persistence. It does not require drama to be effective. It does not require violence to be powerful. The river does not force its way through rock. It finds the path of least resistance, and it follows that path with complete consistency, never deviating, never giving up, and never pausing. Over time, the path becomes a valley, and the valley becomes a canyon, and the canyon becomes a record of millions of years of patient work. The mountains, for all their apparent permanence and solidity, are ultimately subject to this patient work. Every mountain range that was not recently uplifted, and in geological terms, recently can mean tens of millions of years, has been substantially reduced in height and extent by erosion. The ancient Appalachian Mountains were once comparable in height to the modern Rocky Mountains, according to geomorphological evidence. Today they are rounded, gentle ridges, the work of hundreds of millions of years, of rivers and glaciers and other erosional forces, slowly but inexorably wearing them down. The river wins, not through force, through time. This is not a metaphor for human persistence, or a lesson about the virtue of patience. It is simply a physical fact about how this planet works. Water flows downhill. It carries material. It deposits that material somewhere lower. The surface of the earth is continuously being sorted, the highlands being reduced, the lowlands being built up by the quiet, persistent work of rivers. Given enough time, in the absence of tectonic renewal, a continent would be eroded entirely flat, drained by sluggish rivers barely perceptible above the plain. We do not live on a timescale to see this, but we can understand it, and in understanding it, we see the world differently. The valley we live in was carved by a river that has been flowing, in some form, for millions of years. The flat plains of the Midwest are built from sediment that was once part of the Rocky Mountains. The Mississippi River Delta is the current resting place of material that was once a different mountain, in a different place, a long time ago. Everything is in transit. The solid ground beneath our feet is only temporarily solid. It is material that has been moved from somewhere else, and will in geological time be moved again. Water does this, quietly, without announcement, without rest, having traced the full journey of a river from its headwaters in mountains of snowmelt and rain to its final expression in delta and estuary. We arrive at a final question. What does current science suggest about the future of rivers? This is a question that researchers in hydrology, geomorphology, ecology, and related fields are actively working to answer. And the honest response to it has to acknowledge both what is known and what remains genuinely uncertain. One area of growing scientific attention is river restoration, the effort to return modified or degraded river systems to conditions more similar to their natural states, or at least to conditions that support healthier ecological functioning. River restoration can take many forms: removing or modifying dams, replanting riparian vegetation, reconnecting rivers to their floodplains by modifying or removing levees, reintroducing natural sediment dynamics. Research on restoration efforts has generally shown positive outcomes for river ecosystems: recovering fish populations, improved water quality, reestablishment of riparian vegetation, though the degree and pace of recovery varies considerably with the specific conditions and the nature of the restoration. The reconnection of rivers to their floodplains is an area of particular scientific interest. In many parts of the world, rivers have been disconnected from their natural floodplains. by levees and embankments, built to protect agricultural land and urban areas from flooding. This disconnection, while protecting human assets, eliminates the natural functions of the floodplain. Its role in storing and slowly releasing floodwater, filtering pollutants, supporting wetland habitats, and depositing fertile sediment. Current research is exploring how and where floodplain reconnection can be achieved in ways that balance the ecological benefits against the economic and social costs of accepting some degree of flood inundation. Wetland conservation and restoration is another area of active research and policy attention. Wetlands along river corridors, marshes, swamps, oxbow lakes, floodplain forests perform ecosystem services that are increasingly recognized and studied. Carbon storage, water purification, flood moderation, and biodiversity support. Research suggests that many of these wetland systems have been significantly reduced in area over the past century, primarily through drainage for agriculture and urban development, and that their restoration offers multiple benefits for both ecosystems and human communities. Sediment management in rivers is a challenge that will require ongoing research and practice. The global network of dams has fundamentally altered sediment dynamics. In many of the world's major river systems, understanding how to manage the sediment that accumulates in reservoirs through flushing, bypassing, or other techniques, and how to mitigate the effects of sediment starvation in rivers below dams are active areas of applied research. As dams age and the decision is made whether to repair, modify, or remove them, sediment management will be a central consideration. Research in hydrology continues to refine our understanding of how river systems respond to changes in land use, climate, and human management. The development of increasingly sophisticated models that simulate river behavior at scales, from individual channels to entire continental river basins, allows researchers to explore how changes in rainfall, land cover, and human water use might affect river flows and behavior under different future scenarios. These models are powerful tools, but they require continued improvement and validation against real-world observations. A reminder that fieldwork, monitoring, and direct observation of rivers remain as essential as ever. One thread running through current river science is the recognition that river systems are resilient, capable of recovering from disturbance when conditions allow, but that there are limits to that resilience. Understanding where those limits lie and how to avoid exceeding them, while meeting the genuine needs of human communities for water, food, and energy, is one of the central practical challenges. In the science and management of rivers, the rivers of the future will be shaped by decisions being made today about land use, water management, energy systems, and the broader patterns of human impact on the global environment. Current evidence suggests that these decisions matter enormously for the health of river systems and for the communities that depend on them. We have come a long way together, from that single droplet falling on a mountain to the wide, slow delta meeting the sea, from the physics of erosion to the ecology of estuaries, from the ancient civilizations that grew up along river banks to the research labs where hydrologists model rivers with mathematics and computers, from the first trickle of snowmelt to the slow spreading of river sediment across the floor of the ocean. And now, in this final quiet section, let us return to the beginning, somewhere on a mountain. Right now, rain is falling. It falls on rock, on soil, on old forest floor, deep with accumulated leaves and root matter. Some of it soaks in immediately, beginning the long, slow journey through the ground. Some of it runs quickly across the surface, following tiny channels worn by 10,000 storms. Before it, A droplet falls on a boulder, holds its shape for a fraction of a second, and then begins to move. It joins another droplet, and another. It becomes a trickle, and the trickle becomes a thread, and the thread becomes a small stream, and the stream flows downhill through the first V-shaped gorge. It is cut in the mountainside, over a small waterfall, where the rock is harder and more resistant, through a pool of cold, perfectly clear water, where a trout is holding still, in the current, watching for the insects, drifting downstream. That stream joins a larger one, and then another. The water grows, the channel widens, the gradient decreases, the water slows slightly, and takes on color, a faint blue-green, from dissolved minerals, or a tan, from the silt of eroded hillsides. Willows appear along the banks, then cottonwoods. The streambed transitions from rock to gravel to sand, and then the flat land opens up, and the river finds its pace. Wide curves develop across the valley floor. The current slows further. The water becomes heavy with the memory of everything it has carried from the mountains. In spring, the river spills its banks, and the floodplain fills with shallow, warm water, teeming with life. Fish spread through the flooded forest to feed and spawn. Herons stand motionless in the shallows, watching. A beaver's lodge sits in the backwater, behind a natural levee. The occupants safe and dry inside, while the floodwaters rise and fall around them. The flood recedes. A thin layer of fine silt is left behind on the floodplain, almost invisible, perhaps just a millimeter or two. It will dry and crack in the summer heat, and then be covered by growing grass and the leaves of late summer. But it is there, one more layer, added to the long accumulation of floodplain sediment. One more thin page in the slow-written book of the river's history. Farther downstream, the river enters its final stage. The gradient is nearly flat. The channel bends back and forth across a wide plain, one meander cutting into another's old path. The whole river slowly migrating across a landscape it is built from its own sediment over thousands of years. Oxbow lakes dot the plain, the abandoned loops of former meanders, quiet and still, gradually filling with the organic matter of their own wetland ecosystems. And then, finally, the sea. The river meets the salt water with no drama. The current slows. The fresh water rides above the denser salt water for a short distance before mixing. The silt and clay, no longer supported by the current, drift down through the water column and settle, grain by grain, layer by layer. The delta builds outward into the sea, imperceptibly, slowly, but continuously, year after year, century after century, millennium after millennium. The water evaporates from the sea surface, rises into the atmosphere, condenses into clouds, and falls again on mountains. The cycle continues. We began this long, slow journey by asking a simple question. How does something as soft as water carve valleys through solid rock? And the answer, which has been unfolding gradually through every section of this exploration, is with time, with patience, with the absolute consistency of physical laws applied without interruption over scales of time that dwarf anything a human mind can naturally hold. Rivers are not just lines on maps. They are not just pretty features of landscape, not just water sources for human use, not just the subjects of poetry and mythology, though they are all of these things as well. Rivers are active geological systems, the primary agents by which the surface of the earth is reshaped over time. They are the conveyor belts of the water cycle. They are the sculpting tools that carve mountains into plains. They are the builders of coastlines. They are the arteries of ecosystems, connecting mountains to oceans, uplands to lowlands, headwaters to estuaries, in a continuous flow of water, sediment, energy, and life. And they do all of this quietly, without announcement, without urgency. The water simply moves, following gravity, following the slope of the land, finding the channel that carries it most efficiently toward the sea. It has been doing this since rain first fell on this planet, and it will continue doing it as long as there are mountains and oceans and a sun to drive the evaporation that keeps the cycle turning. Every valley you have ever seen was carved by running water. Every river plain was built from the sediment of mountains, now worn to nothing. Every delta was once a mountain, broken down, grain by grain, carried across a continent, and laid down at the edge of the sea to build new land. The material of the earth is never still. It is always being moved, always being rearranged, always flowing in one form or another, from higher ground to lower, from mountain to sea. If you ever stand beside a river, any river, large or small, fast or slow, you are standing beside something that has been at work since long before you were born and will continue its work long after you are gone. The water you see flowing past you has been in many places and has more places still to go. It was a cloud this year and a glacier 1,000 years ago and part of an ancient sea 100 million years ago, and it will be all of these things again in different times as the cycle continues to turn. The rivers of the earth are always flowing, not toward any final destination. They simply cycle continuously through the sky and across the land and back into the sea and into the sky again, not with any particular urgency. They move at exactly the pace that gravity and the shape of the land allow, neither faster nor slower than they need to be, not with any awareness of the work they're doing. They simply flow, and the work happens as a consequence of physics applied patiently over time, and in that patient, persistent, uninterrupted flow, over time scales longer than anything we can meaningfully feel. They have carved every valley, built every delta, built every floodplain, carried every grain of sand that makes up every beach. At the edges of every continent, water, moving quietly across this planet, shaping it, slowly, in the only way that truly enduring work is ever done, not all at once, not dramatically, but continuously, and without end. Hello, calm souls, welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. Now, let's gently explore something many of us have felt, even if we've never named it.